Hi, everyone. I hope that this is a good opportunity for all of us to have a little bit of a review that focuses on ABG interpretation. So I'm just going to start with a little bit of an overview of blood pH. So remember, a solution that has more base than acid has fewer of those hydrogen atoms. That's what differentiates it. And so it has a higher pH. A solution that is basic has a higher pH, and for us it's a pH above 7. We call that base or alkaline. A solution with more acid than base has more hydrogen ions, and so it has a lower pH, and a pH less than 7. So pH less than 7 is called an acid, or it's acidotic. And what we do is assess a patient's acid-base balance by taking a blood sample. Typically, we look at the pH of arterial blood, although there are times when we may look at a venous sample, in particular in situations such as a diabetic ketoacidosis while we're waiting for arterial blood gases to be drawn. We may take venous gases just to look at that venous pH. Okay, so let's look at those basic numbers just to remind ourselves. Arterial blood is slightly alkaline, so remember that number 7 is our differentiation between something that's a base and something that is an acid. Above 7, something is a base, or it's alkaline, and our blood typically runs 7.35 to 7.45. That's a number that you want to keep in your head. We talk about not memorizing numbers. That's a number just to attend to, because you're going to be able to refer to it all the time. pH of less than 7.35 is abnormally acidic, and a pH of above 7.45 is abnormally alkalinic, so it's alkaline. And a pH less than 6.8 or more than 7.8 is inconsistent with life. So there is a range of acceptable pH. Normal, 7.35 to 7.45. Below 7.35, we're looking at something that's acidic or you're acidotic. Above 7.45, we're looking at a person who has blood that's alkaline, and we would refer to that as alkalotic. And less than 6.8 or above 7.8, and that's inconsistent with life. So there's 3 mechanisms by which our body, in this masterful compensatory process, manages to maintain that perfect pH balance. The regulation or compensation mechanism that first kicks in, and it kicks in instantaneously, and it's quite silent in our body, is the use of chemical buffers. So chemical buffers in our body include bicarb, phosphate, and proteins. And a protein would be something very common like hemoglobin that's traveling in our blood. And these chemical buffers act immediately, and they protect tissues and cells when there's any kind of change in that 7.35 to 7.45 range, acceptable range for pH. So what happens is those buffers, those different chemicals, combine with either the excess acid or the excess base, and they neutralize those harmful effects until the rest of our regulators take over. So they kick into gear very quickly. They're used very quickly, so they have a limited range of what they can do, but they kick into gear very quickly while the rest of our body mounts a response. And so we call them often our silent response. The second mechanism that kicks into place, and you can imagine that this happens fairly quickly as well, is our respiratory system. And so what we use is hypo or hyperventilation, so breathing more slowly or breathing more quickly, breathing shallow, and as we typically see, a shallow and rapid respirations, deep and slow respirations, and those allow us to either excrete or retain acids within minutes of a change in pH, and we do that by regulating our levels of carbon dioxide. So what happens is that we actually rely on chemoreceptors that are in our brain, in the medulla of our brain, that sense that change in pH in our blood, and they vary the rate and the depth of our breathing. That the medulla controls our breathing. It varies the rate and depth of our breathing. And so what happens is we breathe faster and deeper. Really fast, deep breathing eliminates more CO2, and our pH rises. So we eliminate more of that CO2, and the pH rises. And so when we're acidotic, our respiratory rate increases to blow off more CO2 to correct the pH. And if this corrects the pH fairly quickly, your body detects that pH change, and then it reduces that CO2 excretion. So it's that feedback loop. As that pH is corrected, our body then detects that correction, and it's going to slow down our breathing. And And then the final level of compensation, the third level, is our kidneys, our renal system. And the renal system excretes or retains acids or bases as needed, and that only kicks in after the other two systems fail to adequately respond. So first of all, remember there's those buffers, chemical buffers in our bloodstream. Secondly, there is our respiratory system, which kicks in fairly quickly. The renal system takes at least 6 hours before it's able to kick in and begin the process, and it may take several more hours beyond that, up to many days, in order to restore pH balance to normal. And so just a couple of things to remember, that as our PaCO2 and our pH change, they move in opposite directions to each other all the time. So as our pH goes up, our PaCO2 goes down, or the opposite, as our pH goes down, our PaCO2 is a measure of it going up. So let's look at the numbers, the basic numbers that we're working with, and the approach to analysis. So when we're looking at a set of ABGs, there are 5 basic steps. The last step is really understanding clinical condition. And the beginning steps are really looking at what those basic numbers are in relation to each other. So first, we're going to check that pH. And if you remember the normal, it was 7.35 to 7.45. And so we asked that question, is the patient acidotic or is the patient alkalotic? Acidotic, less than 7.35, alkalotic, above 7.45. Number 2, we're going to check the PaCO2. And the normal value, and that's, we measure that as a pressure, the carbon dioxide pressure, and it's normally 35 to 45 millimeters of mercury, and we want to see if that PaCO2 is high or is it low. How much CO2 is there, and is it high or is it low? And then we want to check the amount of circulating bicarb. And the normal for the bicarb is 22 to 26 milliequivalents per liter. And again, our question is it high or is it low? So when we look at all of these 3 sets of numbers, our first step is to say what's out of range. And then secondly, how do we look for signs of compensation? Has there been any response to try to bring things back into gear? And when there has been a response, so we look at the value of either the PaCO2 or the bicarb, and which one more closely matches the change in the pH. So if the pH is low, which response, the PaCO2 or the bicarb, more accurately reflects that? If the pH is high, again, which of the PaCO2 or the bicarb more accurately reflects? And it's the measure that more closely matches the change of pH that is reflective of the underlying compensatory process at play. And so we'll do a little bit of practice with that. And then finally, we want to look at the patient's clinical condition. And that's really important. We look at their work of breathing, their respiratory status. And when we're back, this little mini lecture is just talking about numbers. When we're back talking about numbers, there are 2 numbers that really help us to understand clinical condition. That would be the PaO2, so how much circulating oxygen. And that's, again, a pressure value. It should be normally 80 to 100 millimeters of mercury. And we wonder if that's high or low. And then we look at the SaO2, so the oxygen saturation. And that should be within a normal range of 95 to 100. Ideally 100, but 95 to 100 is fine. Again, we're going to say, is that low or is that high? Now, just a reminder about PaO2 and SaO2. And typically, remember, those are that final step where we say, what is the clinical condition? And so when we're analyzing ABGs, we most often focus on those first three numbers, the pH, the bicarb, and the PaCO2. But it's important to understand the percentage pressure of oxygen and the oxygen saturation. So I'm just going to take a second to remind you all of this, only because understanding this basic feature is essential, because the bottom line is we need to understand that oxygenation of our blood. So oxygen travels in the human body by 2 mechanisms. It can either be dissolved in the plasma, so circulating within our plasma, or it can be bound within the hemoglobin. When it's bound within the hemoglobin, it's actually a measure of its effectiveness. So PaO2 refers to the amount of oxygen that's dissolved in the plasma as the pressure value. So when we measure that PaO2, that tells us about the amount of oxygen that's just circulating in that plasma. The SaO2 refers to the amount of oxygen that's bound to the hemoglobin in our arterial blood. So we put that O2 sat probe on. That tells us about the amount of oxygen that's actually in the hemoglobin. and it's the hemoglobin that carries that oxygen to its target cells and enables it to hand that oxygen off so that those cells are oxygenated. That measurement comes as a percentage, and we refer to that as oxygen saturation, and you do that all the time. The relationship between these two values is really important. It's so important because it's all about the dissociation that happens at a critical point. So remember, the PaO2 is the amount of oxygen that's just circulating. Sorry about that. Circulating in the plasma. The SaO2 is our oxygen saturation, which tells us how saturated that hemoglobin is. So how much of its oxygen carrying capacity is filled within that hemoglobin, and the hemoglobin is able to carry it right to the cell where it's able to do its job of oxygenation. And what we want to see is what is the relationship between those two things, how much oxygen we have in the plasma and how much is in the hemoglobin cell. And that's where we look at this, and I know you've all studied it, the oxyhemoglobin dissociation curve. Now, it's a funny thing, again, this course we always say it's about usable knowledge as opposed to always focusing on theoretical knowledge. This is really important to remember because you're going to see a couple of key points. One of them is really all I'm going to focus on in this mini lecture, and that's where you see that top line labeled letter C, where we go across from an oxygen saturation of 90%, tells us that the percentage of oxygen, circulating plasma oxygen, is 60%, or the amount of oxygen in the hemoglobin, it's saturated by 60%. That's really critical, and it's really critical because what you see is a change in the slope of that curve. So if you notice above 90%, the curve is pretty flat. So a saturation between 90% and 100%. There's a very slight change in the PO2 as you move between 90% saturation and 100% saturation. Very little change in the amount of actual oxygen. But as we move below 90%, it's a very sharp drop off. So there is what's called a dissociation. So the oxygen, the hemoglobin molecule is not able to attract the oxygen as much as it would normally be able to do so when it's above 90%. There is a change in the chemical property so that the oxygen is not drawn into the hemoglobin molecule, and it's essential that the hemoglobin molecule actually be able to deposit that oxygen to the cell. So there is a decreased effectiveness of that entire process below that O2 sat of 90, which is the 60%. And that's so critical because the difference between an O2 sat of 90 and 91 is very minor compared to the difference between an O2 sat of 90 and 89. So it's a real cutoff point when we say an O2 sat above 90. We really mean typically an O2 sat above 90. There's other things that come into play, respiratory drive and COPT and other things. But that point of dissociation where the oxygen becomes less attractive to the hemoglobin molecule is really critical in maintaining blood chemistry that enables our body to be oxygenated. Okay, so let's try a couple of examples. First, here, we're just going to go just with the blood. We're not going to tell you a whole patient story. We'll do that in class. pH 7.52, is that high or is that low? PaCO2 of 31, high or low? And a bicarb of 23, high or low? Take a second, you can pause, and I'm going to move on to the next slide. Okay, here's your answer. The pH is high, 7.52 is alkalotic. The patient is in alkalosis. But now we wonder, is this a respiratory alkalosis or is it a metabolic alkalosis? Well, let's look. The PaCO2 was low. Okay, and that can lead to alkalosis. But the bicarb member represents that metabolic process is normal. So the PaCO2, remember our next step is to see which one most closely corresponds with the pH. Well, it's the pH is high and the PaCO2 more closely corresponds to the pH, making the primary cause respiratory, and it's what we end up with is uncompensated. So there's no compensation. Bicarb is in the normal range, so we see no metabolic compensation, and uncompensated respiratory alkalosis. We can talk about lots of causes for that. Typically, an uncompensated respiratory alkalosis is from something like hyperventilation. Let's try again. pH is 7.29. High or low? PaCO2 is 17. High or low? Think back to your standard range. And your bicarb is 19. Standard range, high or low? Take a second, pause if you need to. High or low for pH, high or low for PaCO2, high or low for bicarb. I'm going to move on to the next slide. Okay, this is a low pH, and that low pH tells us that we've got an acidosis. But we don't know what the bigger picture of that acidosis. Now we've got a low PaCO2. Now low PaCO2 leads to alkalosis. We've got an acidosis, but we've got a PaCO2 that leads to alkalosis. We've got a low bicarb, and the low bicarb leads to acidosis. Which one matches? Well, we've got a low pH, and we've got a low bicarb. So the bicarb more closely matches the pH, and that's making the primary cause metabolic. And so it's resulting in a decrease in PaCO2, reflecting a partial respiratory compensation. And so the answer here is we've got a metabolic acidosis, that low bicarb and the low pH are corresponding, and there's a compensatory respiratory alkalosis. The low PaCO2, which leads to an alkalosis, is part of the respiratory system compensating. Okay, try again. pH 7.33. We're getting close to the normal range, but not quite there. PaCO2 of 40, high or low. Bicarb of 20, high or low. Pause and calculate that out, and I'm going to move to the next slide. Okay, our answer. Our pH is low, and I know you're going to remember a low pH is an acidosis. Our PaCO2 is normal. Our bicarb is low, so if we've got a low pH, which causes an acidosis, and a low bicarb, remember that bicarb now is matching our pH. So our primary cause here is metabolic, and you see with the PaCO2 of being normal that we have no compensation now. So we've got an uncompensated metabolic acidosis. An acidosis caused by metabolic conditions with that bicarb, and our respiratory system has not responded. So it's uncompensated metabolic acidosis. Okay, here we go again. pH 7.52, high or low. PaCO2 47, high or low. Bicarb 36, high or low. You calculate, and I'm going to meet you at the next slide. Okay, pH alkalotic, right? We've got PaCO2 and bicarb have both changed. Now, which one is matching closest to the pH? And it's the bicarb. So what we've got is that elevated PaCO2 represents an effort of the respiratory system to compensate for the alkalosis by retaining CO2. And so what would respiratory status look like in that case? Think about it for a minute. And here our answer is that we've got a partially compensated metabolic alkalosis. It's partially compensated because the pH has not returned to normal. If the pH was within the normal range, but the PaCO2 and bicarb were both out of whack, that would tell us that we had a fully compensated issue. But here it's only partially compensated because the pH remains abnormal. And that's the end for today. I hope you enjoyed that. It was pretty quick. We'll go over a few more examples in class. Looking forward to seeing you this week.